Hello everyone, my name is Jonathan Flores, and this activity belongs to the subject of CMOS Digitales. In this case, I'm going to explain the practice of flip-flop. And in this case, we're going to talk about the flip-flop CR, D, and T. So, now I'm going to explain the VHDL module in the test bench used to verify it. So, the VHD. In this case, the entity exposes input S, R, D, and T. The 50 MHz clock is a CLK 50 MHz and asynchronous reset clock. And some outputs Q0, Q0N, Q1, Q1N, Q2, and Q2N, plus clock out. Inside the architecture, I built a clock divider, a 26-bit counter called clock temp that increments on every racing edge of clock 50 MHz, and clock temp number 2 is aligned as clock new. That gives a slower internal clock. I also wrote it as clock out. There are 3 processes, 1 per flip-flop. Okay. For a flip-flop SR, on the racing edge of clock new, it implements the standard cases S equal to 0, R equal 0, hold state, and S1 equal to 1, and R equal 0. Sets Q0 to 1, S equals 0, R equals 1, and resets Q0 to 0. And Q0N is the complement. In the case of the flip-flop D, on each racing edge, Q1 captures D, so Q1N is its complement. In the T section, in this code, it acts as a whole load FF or flip-flop on the racing edge. If T is equal to 0, then Q2 loads D, and if T equals 1, and it holds. Note this is not a toggle on T implementation. Okay, now let's go with the VHT. The VHT code it instantiates the DUT and declares all signals. One process generates a 50 MHz clock by toggling every 10 nanoseconds. Another process in it applies a sequence of S, R, D, and T vectors, and each held for 423 nanoseconds, long enough for many clock cycles, so you can clearly see each flip-flop response in the waveform. The sequences exercise its hold S equal R equal 1, set and reset for as R, data capture for D, and the T control hold load behavior. So the test bench doesn't assert a reset clock, so the divider simply starts from 0 and runs free. So when you view the simulation, we expect Q0, Q0N reacting to set reset per the truth table, and Q1 and Q1N following the on racing edge of clock new, and the Q2 and Q2N loading D only when T is equal to 0 and only when T is equal to 1. So now we're going to run our code to see the waveform. We are select tools, run simulation tool, and RTL simulation. Okay, now we're going to select work and the 2 entities. We're going to select recompile. As you can see, we have 0 errors and 0 warnings. So now we're going to simulate our code. So we're going to select the start simulation. Again, we're going to select work and the flip-flop S VHD test. We're going to select default resolution In optimization options, we're going to select apply full visibility to all modules and select OK. Okay, now we have all of our signals, and we're going to select all of this with the exception of the reset clock. We're gonna transfer to the wave, and we're gonna change the name of each signal. This is just to see more easy in a more easy way or all of our signals. Okay, now we're gonna run the wave, and we're going to select run out for 3 seconds, and then we're gonna stop the simulation. So 1, 2, 3, and stop. And as you can see, we have our signal. We're gonna detach to see in a better way. Okay, so this is the result for the signals. Let me show you in a better way. So this is the web view for all our signals. Now we're gonna simulate in the